grade 12s. So still looking at rates of reaction. I just wanted to do a video for this one because we're going to be looking at graphs a little bit more. So your note is about measuring the rate of reaction, but during this video and writing on the board, I just also want to talk a little bit about recording the rates of reaction. Okay, so basically when I talk about recording rates of reaction, I'm talking about the graphs and how to analyze the graphs. So at the top of your note, you've just got a little reminder about if you have a graph where you're measuring the amount of a substance. Okay, so let's say we had a reaction A plus B goes to C, and we were recording the amount of C being produced as time goes by, then the way you're going to see this graph looking is roughly sort of something like this. Okay, it's going to start without ever dipping. It'll then flatten out. Okay, so it'll start really steep. Okay, it'll start at 0 and it'll be really steep, and it'll get less and less and less steep until the gradient is 0, until it's flat. So I just want to quickly talk this through. It has been on previous notes, but just want to make sure you understand. So it starts at 0. Okay, so it starts at 0 because obviously when you start with your reaction, you have no product. It's just reactants, okay? And as your reaction progresses, the amount of your products increases. Okay, now it is steeper at the beginning, okay, because at the beginning we have a high rate of reaction. Remember, the gradient of this graph represents the rate of reaction. Okay, because rate of reaction is change in the amount of substance over change in y. So it's basically delta y over delta x, which is gradient. That's how you learned gradient in grade 8. Okay, so it's steeper at the beginning because the rate of reaction is higher. Now, in yesterday's note, yes, it was yesterday, in yesterday's note, you learned about the different factors that affect the rate of reaction, and you learned that the concentration of a species will affect the rate of reaction. So the higher the concentration of reactants, the faster your rate of reaction will be, right? Now, as this reaction progresses, you're actually lowering the concentration of your reactants because they're reacting out, they're going away. So as the reaction progresses, the concentration of your reactants decreases, and as a result, the rate of reaction decreases. Because, and we can link this all to collision theory, because you're having fewer successful collisions, because there are fewer collisions in general. Okay, so it starts steep because there's a high rate of reaction. Okay, it gets less steep as the rate of reaction decreases, and then eventually the gradient is equal to 0, i.e. the rate of reaction is equal to 0 when you've got that flat line. Remember, that's a 0 gradient, and this basically means that the reaction is complete. Okay, we're going to have no more C forming basically. So as time goes by, the amount of C present, the amount of my products present, stays the same. So my reaction has stopped. There's no more reaction taking place. Okay, so this graph is it's the one on the left-hand side, the graph measuring increase in products. Let's make a little sort of heading here on the side. Okay, now if we do the same thing, how far down the board can you guys see? Sorry. Like here-ish. Okay. Okay, so if we do the same thing but for the amount of, let's say, A. Ooh. Okay, this is important. So if A were the limiting reagent, you can only base this on your limiting reagent. So let's say A were our limiting reagent. Remember, that's the one that runs out first. Okay, so if A were the limiting reagent, let's do them both on the same graph actually. That's not a bad plan. Okay, so we're going to draw a graph, and then we're going to do A in green, and we're going to do B in black. So B is our excess reagent here. Okay, so what's going to happen is the amount of A, so our x-axis here is the amount of, and we're going to do A, and then we'll do the amount of B as well in a different color. So we're going to start with however much of A we start with, okay? And that amount is going to decrease, right? As our reaction progresses, the amount of A is going to decrease, and the way it's going to decrease is going to be similar to this. It's going to decrease rapidly at first, and then as the rate of reaction slows down, the decrease in the amount of A will sort of flatten out. Okay, so you're going to see a shape that's something like, oh my goodness, that was terrible. Something like that. Okay, where it will flatten out. Okay, and then the amount of B, if we do B on the same graph. Okay, let's say we started with the same amount of A and B. B is also going to decrease rapidly, but it's actually going to flatten out, not on the x-axis, because B is in excess. So the reaction will stop. I feel like there's somebody on my Teams meeting. Sorry, guys. Sorry, that was really weird. There's noises coming from my laptop, and I don't know why. Anyway, okay, so the amount of B will also flatten out, but because it's the excess reagent, there will still be some B left over at the end. Okay, so this is our time again, and we're going to write down all the notes of what we've just said. Okay, so again, it's going to start steep for both of them. Okay, because the rate of reaction is high. Okay, then it's going to become slightly less steep as the reaction progresses, because the rate of reaction decreases. And then we're going to reach a point, we should make these sort of more the same, should flatten out at roughly the same place. Sorry, guys. Okay, so these flatten out at roughly over here. Okay, and when it's flat, that means that the rate of reaction equals 0 because the gradient equals 0. Okay, same thing here. When it's flat, it means the reaction has stopped. And now the reason for them being in different places. Okay, at the end of the reaction, the amount of A at the end will equal 0 because it's the limiting reagent. But the amount of B at the end will not equal 0 because this was our excess reagent. Okay, so the change in the amount of B will stop, we'll get a flat line, so the change in B will be 0, but the actual amount of B that you have left at the end won't be 0 because it's the excess reagent. Okay, so this top graph is for if you're measuring the amount of products. Your graph is going to be shaped like this, and that is why there's all your explanations. And if you're measuring the amount of one of your reactants, your graph will either be like the green one if you're measuring for the limiting reagent, or it will be like the black one if you're measuring for your excess reagent. Okay, so this graph here is for decrease in reactant. Okay, let's just sort of separate those. Okay, guys, I'm going to, if you're not, highly suggest that you copy this down. If you can, if you've printed off the notes, and if you can write small enough, you can just chuck it on the printed notes. You can label the printed notes like this. You'll just have to add another line to the second graph. On the second graph, it's only got this black line. It hasn't got the green line. Okay, so you must pause. I'm going to pause as well, and this is going to be gone when I come back. So if you haven't got it all, quickly pause. Okay, guys, so we're not really reading off the notes. I will refer to the notes, but just for now, I just want to introduce this. When we're measuring rate of reaction, we have to remember what rate of reaction is, right? It's the change in something over change in time. This could be the change in concentration of reactants. It could be the change in mass or of your reactants or of your products, or moles of your reactants or your products, okay? So this change in, the way you're going to define your rate of reaction by measuring the change in something, this depends on the reaction type. Okay, now obviously we've got tons of different types of reaction. The way that you're going to determine how to measure your rate of reaction is mostly going to depend on the phase of your reactants or of your products. Okay, so this depends on your reaction type and more specifically the phase of reactants or products. Okay, so unfortunately for this section there isn't any specific rules that apply every single time. There's no recipe. You have to logic it out depending on your specific reaction. So I'm not yet on the notes, but let's say for example we have a reaction like this where we've got A, which is a no, let's not do that. Let's say we've got A, which is a solid, plus B, which is a liquid, forming C, which is a gas. Okay, if we had a scenario like this, then you can see, right, that we've got a solid and a liquid reacting to form a gas. So we've got options here, just two that come off the top of my head, two different options to go ahead and measure this rate of reaction. Option one, we could let them react in an open beaker, okay, and then the gas will escape, and what we can do is we can put this on a scale and measure the change in mass. Okay, so we can say, well, how is the mass changing? Because A and B, the solid and the liquid, will stay in the container, and as they react, our gas, C, will leave the container and will no longer contribute to the mass. So that's one option of doing this. Another option, and this is on your notes, I will refer to your notes, I'm just going down the rabbit hole first. Another option of doing this would be to let A and B react in a closed container, okay, and what you can do is you can attach a little pipe and collect the gas in something called a gas syringe. Okay, so as I'm trying my best to draw a bit of a syringe here. Okay, so what's going to happen is as this fills up with gas, it's going to force the plunger back, and you can then determine the volume of products being produced. Okay, so like for this scenario, we would be working out the change in mass of the reactants over the change in time. That would be a way to measure the rate of reaction. Whereas in this case, we could be measuring the change in volume of the products over change in time. Okay, so those are just two scenarios, two examples. Based on the phases of your reactants and products, you need to figure out what would be the best way to do this. Okay, you're not going to be asked to do it, but you might in a test or an exam, they'll give you a scenario and they could say, describe one method in which we might measure the rate of reaction. Okay. Okay, so let's actually look at your note now. So first type of reaction that we're going to look at is the gas producing reaction, and that is actually this, what I was just talking about. Okay, so with gas producing reactions, these are basically just any reaction that produces a gas. So for example, metals and acids. Okay, let's actually, yeah, this can go to. Okay, so one type of reaction is the gas producing type. Okay, examples of this are, what did we say, metal and acid. Okay, that produces more than just hydrogen gas, but hydrogen gas is one of the products. The next example on there is a metal carbonate and an acid. We know this one. We did all of these in the last term of last year. Okay, a metal and an acid, a metal carbonate and an acid, all of those guys. So metal carbonate and an acid will produce salt, water, and carbon dioxide gas. Okay, and then the third example on your notes is the decomposition of hydrogen peroxide. Okay, so if we have H2O2, that's going to decompose into H2 gas and O2 gas. Oopsie. O2 gas. Okay, so with any of these gas-forming reactions, gas-producing reactions, probably your best method of measuring the reaction rate is to measure the amount of gas being produced per unit time. And now obviously the volume of gas being produced not going to be entirely accurate because gas is very compressible. Okay, but yeah, if you're keeping the temperature and the pressure constant, then measuring the volume shouldn't be a problem. Okay, obviously then you would measure as the reaction progresses, you would measure the change in volume of what's in your syringe and divide it by the change in time, and that will give you your reaction rate. Okay, then the second type of reaction on your notes was the precipitate producing reactions. Okay, so reaction type 2 is when you have precipitate forming reactions. Now the method of measuring the reaction rate of these is definitely not very accurate, but it is a method. Okay, it is one way of doing it. So the second reaction type is when you have reactions that form a precipitate. So remember all of those that we did in grade 10 where we learned, I can't even remember, the chops now thing, what's soluble, what isn't soluble, when you have a reactant that is soluble and then your product is non-soluble, then that's what happens. Okay, actually let me just remind you. So precipitate is when you have water, right, some kind of solvent, and you have a soluble reactant. Okay, and then what's going to happen is they will react and you'll end up with your water, soluble reactants, more like, okay, and little solid particles which are actually insoluble products. Okay, so it's when you've got soluble things reacting to form something that is insoluble and that comes out as a precipitate. Okay, now the way to measure that, just basically speaking through what's on your notes already, a way to measure that is if you put your flask, whatever it is that your reaction is taking place in, if you go ahead and pop that on a piece of paper, okay, and on that piece of paper you draw an X. Okay, so that when you look at it from the top, you're going to have your glass, okay, your beaker, not your glass, let's be scientific, your beaker, and underneath your beaker you'll have your piece of paper with an X drawn on it. Okay, now what's going to happen is as your reaction progresses, you're going to have precipitate forming. And the more precipitate you have, the less visible that little X becomes until you can't see it at all. Okay, so this is a way of measuring that. Now it's not particularly scientific, you can't really record it as a number, but you can use it for comparison purposes. So you can say, I'm going to compare both of these two reactions, they're both precipitate forming, which one reacts faster based on which one can I no longer see the X on first. Okay, so for this you're going to just eyeball it, it's all written in your notes, you look at it, you observe, you see how quickly does it take before you can't see that X anymore, and you would more use this to compare. Okay, so you'd compare, i.e. for example, let's say I chucked in, okay, let's say I changed the concentration. So in my first experiment, I used a concentration of 2 grams per mole or 2 moles per dm cubed, 2 moles per dm cubed of my reactant. And in my second experiment, I used 5 moles per dm cubed. Then obviously in the second experiment, we would see that little cross disappearing much quicker than in the first experiment. So it's more for comparison, for if you've changed the reaction rate by increasing the temperature or increasing the concentration of your reactants or any of the other tons of ways that you can increase a rate of reaction. Okay, then the third way of doing it is, this is all on your notes, you don't need to be writing this down, is reactions of color changes. Again, observation, as soon as you're doing something where you're just looking at it, where you're just seeing it, it's not exactly 100% accurate, it's more for comparison purposes. Okay, and then reactions of mass changes. So this one is the most accurate of all of them. So I actually do want to write it down. It's very important. Sorry, I'm going quite quickly. I just did a Teams meeting, so now I'm in like I need to hurry mode so I don't waste everyone's data, you know. But I suppose this is a recorded video, so I can take my time. Okay, so this is reaction type 3. No, 3 was color change, okay? You don't need to know the numbers, it's not important. These are just examples of reaction types and how you could go about measuring the rate of reaction. So the fourth one is when you have a mass change. Okay, so the gas producing reactions, the ones we looked at first, most of those you're also going to see a mass change, right? Because you've got something going from one phase to another phase. But for this, remember, very important, we learned it in grade 10, the law of conservation of mass says that the mass of your reactants will equal the mass of your products, okay? The overall mass, the overall amount of matter in an isolated system is conserved, regardless of any physical or chemical change, in an isolated system. So, in order for us to have a mass change and not be breaking the laws of physics, it means that we must be in a scenario where we do not have an isolated system. Okay. Okay, so what that means basically is you've got to let the gas escape, which means in real life, you either make sure you're dealing with something that is not a harmful gas. If you are dealing with a harmful gas, you would have to do this experiment inside a fume cabinet, okay, or a fume closet, which is something we don't have at school, but when you go to varsity, you'll see them.